If we keep moving here, let's work through an example here. I'm going to I'll go ahead and draw it out. So if we work through an example, this one is similar, but this one has a distributed load and it's a pin and roller. So we're going to find shear moment, shear normal and moment at point C, D, and E, and this is our diagram here. So go ahead and pause here so you can copy this down so the video doesn't get too long. All right, now that you've got that copied down, what is our first step when we're trying to find these things? Well, we're going to make a cut at this beam at these 3 points, and we're going to draw part of the beam. I normally just draw the left-hand side of the beam. That's me. You can draw the right-hand side if you prefer. But what's the first thing we've got to do? I'm hoping you say find the reaction. So go ahead and pause again. I'm going to pause it here. Go ahead and find your reactions. Okay. Hopefully you've got reactions now. Again, as you're seeing, you need to be able to do this very quickly. Write the equations out if you're comfortable with the math. Wouldn't necessarily have to for reactions, especially when you've got 2 reaction Y forces with a single force in between, splitting them evenly. That just means this 2,000 newtons gets divided between these 2 Y reactions. There's no X direction, so you end up with no X direction force. But again, sum of moment, sum of force in the X and Y will get you to that conclusion. Now, if we continue from there, so what is our first step? What are we looking for? Well, again, I'm looking for the shear normal and moment, bending moment at point C, D, and E. So I need to make a cut at point C, and a cut at point D, and a cut at point E, and analyze each of those. Go ahead and make your cut at point C. You should be able to do that based on what we did in the previous video. So go ahead and do that. Pause it here. Make your cut at C. See if you can find normal, shear, and moment at point C. So this is what we have at point C. Again, point C is 2 meters out here. So I'm going to draw a free body diagram where I've cut right there 2 meters in. There's nothing in between point A and point C, so it's all blank in between there. So the only thing I've got is my reaction force at A. You can draw AX here. We've already found it to be 0. You could draw AY just simply as AY. We've already found AY to be a positive 1,000 newtons, so you can just draw it right there as you've already found it. And then we've cut through at point C. That exposes shear, normal, and moment. And we've got to find those. Now there's nothing in the X direction other than this normal, so that simply is 0. The shear, you can see, is down. This is our standard sign convention when I'm drawing the left-hand side of the cut. Normal is positive X, shear is negative Y, bending moment is positive counterclockwise direction. So, sum of forces in the Y, we get shear of 1,000 newtons. And to counteract this one, and bending moment, some moments about, and I should say point A. I didn't take moments about point C. Some moments about point A should add up to be 0. You've got your bending moment here. I've drawn it positive. Minus this shear force going down at a distance of 2 meters. Solve. Okay. Now, I'll work with you here about the cut at point D, since this is the first time we've done one where, because here we're cutting under the distributed load. We're cutting inside a distributed load. Right? So when we did our reactions, the entire distributed load was applied over this 4 meters, 500 newtons per meter. So I had the entire 2,000 newtons was being applied here. But when I cut through here, I'm not applying the entire 4 meters worth. I'm only applying 2 meters worth. Now, you can go ahead and condense that down to a single force if you like. I tend to just go ahead and leave it as a distributed load myself, because when we go to the next step, and that's going to be shear moment diagrams, you might find it's a little bit easier to figure those out if you have it distributed still. So what do we got here? This is lecture 14. This is page 4 of something. Okay, so I've got 4 meters until this distributed load with an intensity of 500 newtons per meter occurs, and point D is only point D is 2 meters in. Again, I'm cutting right here at point D, so that's 4 meters to the distributed load, 2 more meters into point D. So I have 2 meters worth of this distributed load. And when I've cut through, I've now exposed shear at point D. You could, it's arguably whether you just want to say that normal is going to be 0. And then I've got a bending moment at point D. So these are now the things I'm looking for. Okay. And you could say AY is equal to 1,000 newtons. I should have just wrote 1,000 newtons like I did this one. I don't know why I wrote AY there, but either one's technically correct. We've got a value for AY. I'm just going to write sum of forces of X equal to 0 right there because I don't need a lot of room to just simply say that the normal at point D is 0. There's one answer. Sum of forces in the Y direction. That's also going to be 0. I've got the 1,000 newtons over there at point A in the positive direction. In the negative Y direction, I've got the shear at point D. And then I need to find the area of this little rectangle there. I'm going to write this down here. I could have left it there. I'm just going to write it down here. Sum of forces in the Y direction equals 0. 1,000 newtons minus the unknown shear that I'm looking for. And again, I need to find the area of this rectangle. Well, it has, it's in the negative Y direction, 500 newtons for every meter, and that's occurring over a distance of 2 meters. Or you could just write 1,000 newtons there if you like. So I've got 1,000 positive newtons. This is going to generate 1,000 negative newtons. Notice the shear at point D is not needed. There's actually no shear force at point D. Okay, interesting. Well, what do we do from there? Sum of moments, because I got to find this bending moment. I could take the moments about point D if you really like. I'm going to go ahead and take the sum of moments about point A just out of habit. It's kind of easy to write that equation. All the positive moments, I've only got one positive moment there. That's this bending moment that I've exposed at point D. I do have some negative moments. So I have minus the shear at point D, and it's out at a distance of 6 meters from point A. Now, yes, I know the shear is 0, and you could just write this as a 0 if you like, but just what I would suggest to you is doing it systematically like this is going to make the next thing we're going to do a little bit easier. Okay, so we'll see that. So I got shear at point D now is we've already said is 0, so this term's going to be 0. But I do have one more thing causing a moment. I've got this distributed load causing a moment. It's causing a negative clockwise moment, so that's a 5,000 newtons per meter. I should say a negative or clockwise moment. That is being applied over a distance of 2 meters. So this gives me the force, which is not a moment. I need to know the moment. So this gives me the force. I need to know the distance. How far out is the center of this rectangle? Well, the center of the rectangle is right in between the 0 and the 2. It's going to be right here at 1. Right, and it's not just 1 meter, it's going to be out in here somewhere, 1 meter past the starting point, which is 4 meters from point A. So it's a total of 5 meters to get to where the center of this rectangle would be. The actual moment arm is going to be 5 meters. So that's the kind of the hardest part of this. If you're not used to that, the hardest part of this is figuring out how do I find this moment arm when I leave this load distributed. So if you had to go ahead and condense it down to a single force, you could. It's, put 1,000 newtons right here, 5 meters from point A, and then that is okay. You're more than welcome to do that. So what do we get here, right? Well, let's solve for that moment at point D. Well, this guy is 0. Okay. I'm going to have 500 times 2, that's 1,000 newtons. times 5 meters. It gets added to the other side of the equation, so that ends up being 5,000 Newton meters is going to be the value there for the moment at point D. So that's my third answer at point D. And again, what are we looking for? The problem wanted to know, find shear, normal, and moment at point C, D, and E. So I've got 2 of those. So it's asking for 9 things. 3 times 3. I've found 6 so far. Let's find these last 3. Okay. So if I find the last 3, well, if you want, go ahead and pause here and see if you can do it on your own, and then come back. All right, so go ahead and pause and see if you can find normal, shear, and moment at point E. All right, so remember, we're trying to find shear, normal, and moment right there at point E. So we're going to draw a free body diagram where we've cut through the beam right there at point E. So that's 10 meters out. I mistakenly wrote 6 and 2 earlier. It's actually a total of 10 meters out if you go back to the original diagram measured to point E. So that's my mistake, but I've got it corrected here. I just chose to go ahead because I'm now outside of the distributed load at point E. I've gone all the way through the distributed load. I'm now past it. So we've encountered the entire distributed load to get to point E. So I go ahead and, for me personally, I go ahead and condense it down to a single force at that point. I still have this reaction at point A that's being applied. And again, I've cut through at point E, exposing shear, normal, and moment. The normal is the only force in the x direction still. That's perfectly okay. Sum of forces in the x direction equals 0 is equal to NE. Right. Sum of forces in the y direction. I've got 1,000 newtons going up, 2,000 newtons going down, and also VE going down. So when I solve for VE, these add up to be a negative 1,000 newtons, and that's what we're left with at point E is our shear force. And then finally, at the moment, as long as I get the distance right, which I didn't initially, you can take your sum of moments about any point. I just stay pretty straightforward and call it A, set it equal to 0, reaction moment. I've got this 2,000 newtons causing a clockwise rotation, so that's negative. As it's drawn, the shear is also causing a clockwise rotation. I know it's actually a negative 1,000 newtons, but I go ahead and leave it in my equation. This is how I manage it, so I don't have to, well, which sign is it, and how many signs do I have, and how many negative signs. I've drawn it in the negative, so I'm going to add it in my equation as a clockwise motion because it's causing a clockwise moment, so it's negative here, times its moment arm 10 meters. And so when I solve for this then, move everything else to the other side of the equation, well, 2,000 times 6 gives me 12,000 Newton meters, that's this guy. Plug in a minus 1,000 newtons for VE, right? So VE 1,000 minus 1,000 newtons. So this gets added to the other side of the equation, so plus a negative 1,000 newtons, add a distance of 10 meters to that shear. That sum gives me a positive 2,000 Newton meters. All right. I think we'll probably stop this video here, and then we're going to start talking about drawing diagrams, tracking this. What does this look like over a particular distance x? All right. That'll be our next video. We're going to talk about shear moment diagrams.